introduce one of the topic, introducing like Suzuki coupling, something like that.
Yep.
Because one of our lecturer just came back from Germany, and he's working in organometallic catalysis, and he would like to introduce one of the topic related to that into the practical work.
Okay, yeah, well, I do cover Suzuki's and other transition metal stuff in here as well today. It's just sort of, but it's, yeah, obviously that's, I tried to do it in a way that doesn't necessarily require too much background information on all the bonding in the, you know, with the metals and that sort of thing. So hopefully it can be, you can explain it. And...
Yeah. Like it's very important topic, but yeah, I'm not sure with the facility, because like probably we can still do that kind of reaction, but by using traditional one, because I think it will require some kind of dry condition, yeah, Trent?
Yeah, well, except for the Suzuki, but yeah, the others do.
Yeah. We'll check. Sorry? Yeah,
I was just going to say.
I will check the student first to make sure that they will join at 10. So we have Dr. Jamal as well joining us. Jamal, hello. Not sure. It's not currently join us. So how's Melbourne actually this day during the pandemic? Like, is the research, I mean, laboratory works running like as normal, or there's some limitation?
Yeah, so for us, we have 50% capacity.
50% capacity, yeah.
Yeah. Yeah, so it's a little bit restricted, but we can also work flexible hours or sort of outside of hours as well sometimes if we need to do extra stuff. So it's probably not going to change for another month or so. Because our case numbers are sort of tracking up.
Yeah. But there's zero number of like infected people in Melbourne?
No, we're actually sort of starting to get high or close to 2,000 cases a day again.
Yeah, again.
Oh, this is actually, so say again, this is probably the worst we've had it since March last year. So yeah, but vaccination numbers are going up. So.
Okay, yeah. How's like the vaccinated process there? Is it like all of the Australians have been like vaccinated or not?
I think with maybe 80% of people have had one dose.
Oh, one dose. First dose,
50% of people aged over 16 have had 2 doses.
2 doses, yeah.
So obviously, you know, teenagers and small children aren't covered. So that's sort of where our concern. I've got a 3-year-old, so sort of keeping her home at the moment so that she's not out being exposed. What's it like in Indonesia?
Yeah, in Indonesia, like not sure how many percent, but they will like started the vaccinated for the medical people first, and then teacher, and then now I think all of the citizens have been vaccinated. Some of the citizens that have not been vaccinated, probably the one with some of comorbid disease. So yeah, I think most of the students, including university students, have been vaccinated. Yeah, and only some probably, yeah, people, citizen with some comorbid disease that have not been vaccinated. But because Indonesia like has many islands, so the distribution
Yeah.
of vaccine is can be some issue as well. Yeah,
Yeah,
in
yeah, I
in the
imagine.
city, probably most of them have been vaccinated. Yes.
Yep. Yeah, hopefully there's an end to it soon.
Yeah, really hope. Yeah.
Yeah.
Yeah, I heard that like in Australia, they have been like 5 times for lockdown. Yeah.
Yeah, yeah. So I think Melbourne, with in excess of 200 days, we've been had some sort of restrictions imposed.
Oh,
So yeah, it's quite but they haven't been. I mean, it stops a lot of people from going to work and being able to work. So a lot of people are being affected by that. But you can still go out and get some takeaway food or something like that, and still go out and exercise and things like that. So it's not like we're only allowed to stay in our houses and that sort of thing. So we can get out to some extent.
Yeah. Yeah, in our university, even though like most of the lecturers and students have been vaccinated, like we are still doing some online teaching.
Yep.
And for the student who has to do some research, they will be allowed, particularly for doctoral and master students. But for bachelor degree who would like to do the research, they need to come. Yeah, there's some criteria to join the lab. So yeah, still there are some restriction for them.
Yeah. Yeah. So just a quick question, when I'm doing this, will you still be able to see me? I'm not sure what you can see at your end.
To see like your screen?
My screen, but also can you see me? Yeah, okay. All right. I should just say, just in case.
Yeah,
that's good. I just sort of should say, every now and again a cat might jump across the camera. So
yeah, the camera is good. I can see you and I can see your slide as well.
Yeah. But if you see a tail walk past, it's one of my cats jumping in front of the camera. Hopefully that doesn't happen too much.
Yeah. Okay. Ada sini bule. Tapi so we still have another 2 minutes for waiting some of students to join. Yeah.
Yep.
Rani.
Bu Ika. Halo Bu Ika.
Lagi.
Assalamualaikum Bu. Yes.
Harus susah masuknya.
Sekarang udah bisa masuk ya. Ibu mau bicara dulu, berbincang dulu sama Dr. Trent Aston.
Nanti enggak.
Iya.
Baru kontak heula bade.
Ya,
Bade ieu heula.
Oke, siap Ibu.
Siap.
Ya Bu, sudah jam 10, ini baru 62 ya. Kita mulai aja gitu atau nanti menyusul ya?
Dokter itunya udah datang?
Udah, Dr. Trent Aston sudah ada, sudah join.
Belum kelihatan ada. Ini teh Zoom-nya teh nggak tahu tuh. Background juga jadi nggak bisa gitu.
Gitu?
Iya.
Ya.
Dokter
Nanti kita mulai aja barangkali ya, karena Dr. Trent Aston sudah nunggu ya, nggak apa-apa? Ya. Okay, Trent, I think it's has already 10:01, more than 1 minute. I think we can start ya.
Yep, I'm ready.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Yeah, good morning to all of the participants in Indonesia, the student and also the lecturers, and also good afternoon to Dr. Trent Aston in Australia. So welcome in third guest lecture for the subject of synthesis of organic compound, where today we have a special guest lecturer from Australia, Dr. Trent Aston. Dr. Trent Aston today is going to give a lecture entitled Carbon-Carbon Bond Formation. This is one of the interesting topic for us when studying organic synthesis. But before we are hearing the lecture from Dr. Trent Aston, I'm going to read the curriculum vitae of Dr. Trent Aston. So Dr. Trent D. Aston lives in Victoria State, Australia. He did a bachelor degree in Deakin University, and also he got honors degree from a different institute, which is Monash Institute of Pharmaceutical Sciences. And from this institute, Dr. Trent Aston also obtained his PhD degree. So his research experience has been expanded by joining several postdoctoral research in Boston University, USA in 2008 until 2009, and postdoctoral research in Monash Institute of Pharmaceutical Science from 2009 until 2010, and from 2010 until 2018, he joined postdoctoral research in Deakin University. From 2018 until present, he is working in Walter and Eliza Hall Institute of Medical Research as Senior Research Officer. There are so many results that has been published by Dr. Trent Aston in many high-impact journals, including Chemical Communication, Journal of Organic Chemistry, Cells, Langmuir's, Journal of Medicinal Chemistry, Antimicrobial Agents, and then SynLab, and many high-impact journals. Besides his research experience in organic synthesis, he also has a university teaching experience. He has been a lecturer in Deakin University from 2011 until 2017 in the subject of medicinal chemistry and also in organic chemistry. And also in the last 4 years, he ran a heterocyclic chemistry module as part of the Deakin Biomedical and Forensic Science Honors Program. So many achievements that have been resulted by Dr. Aston. So I think that's some of curriculum vitae that I can read. Now we will be hearing the lecture by Dr. Aston. So to Dr. Trent Aston, time is yours.
Thanks, Rani, for that kind introduction. So I'll just one last double check that the slides are visible and you can hear me. Yeah, excellent.
All good.
All right. Well, thanks very much for the opportunity to speak today and discuss some CC bond formation chemistry. It's a very exciting opportunity to be able to address your organic chemistry class. So, did that advance the slides? Sorry. just having... Sorry, did the slides change?
No, it's still in the first slide. This is the title slide. Oh yeah, it's moving now.
Yeah. Sorry about that.
Okay.
So firstly, I'd just like to talk about carbon-carbon bond formation. As you could appreciate with organic chemistry, carbon-carbon bonds are found everywhere in just about all organic, or in all organic molecules. So at some stage, if you pursue a career in chemistry, if you're going to make an organic molecule, you will most likely have to make a carbon-carbon bond at some point. And if we wanted to if you don't believe me in how important carbon-carbon bonds are, we just got to search the Nobel Prize website, in particular look at the chemistry Nobel Prizes, and there are a number that have been awarded to chemists who have looked at carbon-carbon bond formation chemistry. And these include Victor Grignard from 1912, Otto Diels and Kurt Elder in 1950, George Wittig in 1979, and more recently, in 2005, one was awarded for ring closing metathesis or alkene metathesis reactions, and 2010 for palladium catalyzed cross couplings, and even as recently as last week, Benjamin List and David McMillan were awarded the Nobel Prize in Chemistry for their contributions to asymmetric organic catalysts, which involved some CC bond formation chemistry. And a number of these, or the chemistry that resulted in the award of these prizes, will be discussed in today's lecture. So to start with, I just want to introduce what we'll be looking at in the first section. And that will be just introducing organometallic reagents and what they are. We'll discuss their formation and the typical reactivity you expect to see from an organometallic. And we'll also show that how the choice of metal in the organometallic reagent can unlock a diverse range of different chemistry. So after this section, you should have an understanding of the structure of organometallic reagents. You should learn how organometallic reagents can be prepared, and also understand how these reagents can be used to form carbon-carbon bonds. So normally when we think of carbon in chemistry, we think of it as an electrophile. So you might have highlighted in red here, I've just highlighted two elements of interest, oxygen and chlorine. I've just showed the Pauling electronegativity of these elements. So both of these are above 3. And if you compare that to orange shown in red, carbon shown in orange, the electronegativity of carbon is 2.5. And so what this means is that if you bond a carbon to an oxygen or a chlorine, you end up getting the distribution of electrons towards the more electronegative atom, which means your carbon is electrophilic, also has a partial positive charge. And that means a typical reactivity of the carbon with these reactions is as an electrophile, and you normally might react the carbon with another nucleophile, something with electrons like a nitrogen or an oxygen of some sort, but not typically a negative carbon. If we consider organometallic compounds, firstly we want to just define what these are. So an organometallic compound simply contains a carbon to metal bond. Unlike carbon to oxygen or carbon to halide bonds, the electrons in the bond are polarized towards the carbon in this case. And we can see that from in the green boxes, we've just highlighted lithium and magnesium, who have electronegativities that are less than carbon. So that means when those atoms are bound to a carbon, the majority of the electron is polarized towards the carbon, and we end up having a partial negative charge on the carbon. So our organometallics are typically nucleophilic as a result of this. Also, as a consequence of the extra electron density at the carbon, they are also quite strongly basic reagents, which is another key feature of these reagents. So the common organometallics that we'll discuss in this first section are the organomagnesium reagents, which are also called Grignard reagents, organolithiums, and we'll briefly touch on organocopper. But this is not an exhaustive list. There are many other organometallic reagents that can be formed. So just another way of showing this, this general structure I've included here of a Grignard reagent, just to highlight what I mean about the negative charge on the carbon. Here we can see we have a magnesium, which is in between an R, which is a general representative of a carbon group, and X, which is just a general representative of a halide. Given that the magnesium has has a lower electronegativity than the adjacent two atoms, it becomes partial positive in the bonding of these atoms. And as a result, we can see this delta negative charge on the carbon, which gives these compounds their reactivity. So, so that's just the basic structure and function of the organometallic reagents. So next I wanted to just go into how we might form some of these organometallic reagents, and then we'll discuss some of the reactions of Grignard reagents with different functional groups such as carbonyls, epoxides, nitriles, etc. And then we'll cover some of the selectivity you can achieve by using organolithium reagents, and follow that with a short slide on organocuprate reagents. So to form organometallic reagents, we typically start with, we can start with an organohalide. So this is quite interesting given that our organohalides, as I mentioned earlier, are typically regarded as a carbon electrophile. But with the addition of metals to the bonds, you can actually generate a carbon nucleophile. So it just shows you how versatile the organohalides can actually be in this chemistry. So there's a number of ways that we can form organometallic reagents. And just on this slide, I've shown an oxidative addition preparation for both Grignards and organolithiums. So the top scheme, we have, starting on the left, we have an organohalide represented by Rx, where R can be an alkyl group or an aryl group, so a phenyl ring, and our X can be a halide such as a chlorine, bromine, or iodine. And in this chemistry, we'd actually take magnesium metal in a solvent such as THF or ether, and that magnesium metal, which has a oxidation state of 0 as it's drawn there, will actually insert into the bond between the carbon and the halogen atom. And during that process, the magnesium goes from an oxidation state of 0 to an oxidation state of 2. So that's why, so it's oxidized during this process, and that's why we're calling it an oxidative addition, because the magnesium is oxidized and it adds into the carbon halogen bond to give you your so-called Grignard reagent. On the bottom arrow, we can see a similar process for organolithium formation. Here we have our generalized organic halide. In this case, we treat that with a lithium metal in a solvent such as hexane or THF. In this instance, we generate, the lithium is oxidized from a 0 oxidation state to an oxidation state of 1. And I apologize, I just noticed that in the organolithium shown on the bottom right, there shouldn't be an X there. So what happens, the lithium actually replaces the halide in this instance, and a second equivalent of lithium is oxidized to give the lithium cation, which forms the lithium halide salt, which I've shown on the left here. So in addition to these oxidative addition methodologies, we can also generate alkyl lithiums via deprotonation. So a number of organolithiums are actually commercially available, such as the one shown on the top arrow, which is butyllithium, which means we don't actually have to generate a lot of these alkyl organolithium compounds ourselves. So a lot of these can be bought off the shelf and be used to generate organolithiums of choice, depending on the desired chemistry we want to do. So as mentioned before, because of that carbanion-like structure to the organolithium, the organolithiums are quite strongly basic. And so they can deprotonate acidic or even weakly acidic bonds. So in the top line here, we're actually looking at deprotonation of a terminal alkyne. So an alkyne we consider to be an acidic carbon, although in terms of your standard acid-base chemistry, which goes on a scale of 0 to 14, the pKa of this alkyne is actually 26. So it's actually not what we consider to be too acidic, but in the presence of a strongly basic reagent like an organolithium, we can actually deprotonate that terminal proton to give the 1-hexynyl lithium species shown as a product in that reaction. And as the side product of that reaction is the protonated butyl lithium, which in this case is butane. And we can see just below that, we're just indicating that the pKa of butane is about 50. So you've got a number of order of magnitudes more basic, than that alkyne. So that's why we can drive the reaction to that point. Another similar reaction on the bottom uses this sulfur-containing compound, which is called a dithiane. So again, we have a weakly acidic compound here with a pKa of about 31. But again, this is no match for the basicity of the butyl lithium, and we can actually deprotonate the proton which is adjacent to the 2 sulfur atoms. And this is actually a very important reagent or process in organic chemistry, because that alkyl lithium, dithiane alkyl lithium, is actually the equivalent of a masked acyl anion compound, which I've tried to show here on the right. So here we've got an equivalent where there is a negative charge on the carbon end of a carbonyl compound, which is the complete opposite of what you would normally expect, because that bond is normally polarized to the oxygen and the carbon is actually typically has a partial positive charge. So the organolithiums in this case can actually reverse the reactivity of some carbonyl compounds. Another important formation of organometallics is called a halogen metal exchange. And in this case, we will take one halogenated organic compound, which I've just shown here on the left as bromobenzene as an example, and we can add our butyl lithium to a solution in THF at cold temperatures to that bromobenzene. And in practice, what essentially happens here is that the lithium and the halide swap places. That's the simplest way to think about this. So we end up actually with this phenol-lithium compound, shown as the first reaction product, and also as a side product, the bromobutane. And you could probably look at these products on the right and say, well, why can't we add those two together to generate our starting materials? And yes, that's a reasonable argument, but what we find with the formation of organometallics through halogen metal exchange is that it actually favours the more stable organolithium, and that is usually dictated by the pKa of the carbanion form of the organolithium. So in this case, the pKa of the phenol-lithium is approximately 37, which is much lower than the pKa of the N-butyl lithium shown on the right. And that is the driving force for this reaction. Another way of generating organometallic reagents is by converting one organometallic into another organometallic. And that process is called transmitylation. So what we've shown in this reaction is, again, another halogen metal exchange with butyl lithium and this aryl bromide compound. And that can give us our organolithium. If we add something like zinc bromide to that reaction mixture, then that can actually transmetallate with the lithium to generate an organic zinc compound in this instance. And in these cases, what we find is that formation of organometallic compounds usually proceeds towards the organometallic with the lower electropositive metal. So the metal that's less likely to form salts in solution. So the byproduct of this reaction is lithium chloride, and that's much more stable salt than the zinc bromide. And this transmetallation is actually something that we're going to come across later in the lectures when we start talking about palladium catalyzed chemistry. So that's the general preparation of organometallic reagents. Next, we want to consider what we can do with these reagents and how can we use these to make carbon-carbon bonds. So first, I'll just reiterate that the typical properties of organometallic reagents dictate that this is what we call an informal carbanion. So in terms of mechanisms and how we draw out the reactions, we tend to think of these as a carbanion for simplicity. And remember, this organometallic bond is very polar, almost ionic with the share of electrons towards the carbon. And as a result, they are strong bases, but also strong nucleophiles. Unfortunately, the reaction of organometallic reagents with alkyl halides is not as straightforward as you might think. It probably would be the easiest reaction you could probably conceive with these compounds. But what happens with Grignards, for instance, is they actually react quite poorly with alkyl halides. So we don't usually use that as a method. In fact, Grignards, we typically talk about reactions with carbonyl compounds or carbonyl-like compounds. Organolithiums can undergo some SN2 type reactions, but they're often plagued by competing side reactions, which come about by competing reactions such as elimination. And again, both of these types of organometallics tend to react well with carbonyl compounds, but we'll cover more of this shortly. One useful reaction you can do is the reactivity of your organometallic with a proton source. And this results in the reduction of the alkyl halide. So just shown on the bottom reaction here, where we start with a bromobutane, where we can use an oxidative addition reaction with the lithium to get our butyl lithium organometallic. We can then use a variety of proton sources to actually generate, in this case, butane. So we've been able to take this alkyl halide compound and convert it back to its base hydrocarbon. And given the strong basicity of the organometallics, we can use such reagents as water to quench or to react with the butyl lithium to give up a proton. We can also use alcohols, carboxylic acids, and also amines. And one interesting amine that we'll actually come across later in some of the slides is diisobutyl amine. Now that again has quite a high pKa of 36, but that is no match for the strength of the butyl lithium. So we can use butyl lithium to deprotonate the diisobutyl amine to give this species shown in the right-hand box here, which is known as lithium diisopropyl amide, or LDA, which is another strong base we use commonly in inorganic reactions. And that will come into some of the slides later on. So next we wanted to talk about some of the typical reactivity you see with organometallic reagents, and we'll talk about this in the context of Grignard reactions to start with. So one common reaction is to take a ketone or an aldehyde, just represented by this general carbonyl structure here, and treat that with our organic organometallic of choice, represented by an aryl Grignard on the top line here. And what we get in these instances is addition to the carbon end of the carbonyl bond, as you would expect to see for a normal 1-to addition type reaction. And another thing you'll notice here is we've actually got a step in the reaction where we add water or acid to it. And that is just to quench the reaction typically and generate our final product. Because our organometallics are so basic, and we've shown on the last slide that they can react with water, we actually have to perform these reactions in the absence of water under anhydrous conditions to generate our products. And to get the final products and get rid of the magnesium, we usually add water to the reaction at the end to give the, in this case, the alcohol. So the mechanism of this reaction is just shown here. So oops, sorry. So in the first step, we can see that we're actually getting coordination of the oxygen of the carbonyl to the organometallic. And in some instances, we can form more complicated organometallic species, shown here with this 6-membered ring, which results in transfer of a carbonyl group from one organometallic species to the carbon of the carbonyl, the ketone in this instance. And that then generates this magnesium salt of our desired alcohol, and also forms magnesium halide as a byproduct. And when we then work up this reaction or quench it with water or acid, we can generate our desired alcohol. So ketones and aldehydes are very reactive towards Grignard reactions. So this is quite a reliable reaction and a good source of a good way to synthesize tertiary alcohols. And just another, on the bottom line here, we've just got an alternative mechanism where we just, depending on what your R group is, sometimes you can just have direct addition to the carbonyl group without the formation of that more complicated organometallic sort of cluster shown on the top row. So one thing I just wanted to keep in mind from this slide, in addition to the fact that we can convert ketones and aldehydes to alcohols, is that the ketones are very reactive towards organic or Grignard reagents. And that becomes especially important when we're trying to make ketones using Grignard reagents. So one might think that you could take an ester, as shown in this reaction here, and react that with a aryl Grignard reagent to just form this ketone shown as an intermediate in this reaction pathway. And as we just discussed, the ketone is actually quite reactive towards the Grignard. In fact, it's more reactive than the ester shown on the left. So in practice, what actually happens is that when you form the ketone before another molecule reacts with the ester, the ketone will react with excess Grignard reagent to give the tertiary alcohol. In this case, where we've added 2 aryl Grignards to that 1 carbon group. So this is a nice way to make, another nice way to make tertiary alcohols from esters, but unfortunately it's not a good way to make ketones using Grignard reagents. So our mechanism for this one is just a nucleophilic acyl substitution reaction where we have attack of the carbon group on the Grignard onto the carbonyl carbon, and we get the electrons moving up to the oxygen to give our tetrahedral intermediate. This tetrahedral intermediate then collapses down to kick off methoxide in the form of this magnesium methoxide salt to generate our ketone intermediate, and this then reacts using the same mechanism shown in the last slide to generate our tertiary alcohol, which we can then get on workup. Again, taking advantage of some of the slow reactivity of esters with Grignards, we can actually use a Grignard reaction between a Grignard and acid chlorides to generate esters, which is what we've shown in this reaction scheme here. Here we have our Grignard reaction on the left, reacting with this acid chloride-like compound to give an aromatic ester shown here. And just below, this again is another nucleophilic substitution, acyl substitution reaction where we have our Grignard here represented by this carbanion with the arine group attacking at the carbonyl end of this, the carbon end of this carbonyl to generate a tetrahedral intermediate. This tetrahedral intermediate can basically lose one of two, or can decompose in one of two ways. It can lose the chloride shown in the blue arrow, and that gives directly the reaction product. It can also lose the methoxide shown by the orange arrow to give you an acid chloride. This acid chloride is still reactive towards the methoxy that you've just kicked off. So that can actually reform this tetrahedral intermediate, which will eventually lose the chloride and give you the product. So if you keep the temperature of this reaction low, the equilibrium will eventually lead to the formation of your desired ester product. And again, if the reaction temperature is kept low, you won't get any further addition to the ester, and so you won't get this over addition to ketones and then also tertiary alcohols. Which we have sort of also shown here below, where we can take Grignard and react with the acid chloride. So at higher temperatures here, we end up generating, again, a ketone, which is reactive towards another equivalent of the Grignard reaction, and we end up getting a tertiary alkoxide or alcohol for this reaction. Another useful reaction with Grignards is to quench the Grignard reaction with carbon dioxide gas. And this reaction results in carboxylation of your Grignard reaction. So this is shown in this first arrow here. The Grignard adds to the carbon of the carbon dioxide to generate this metal salt carboxylate intermediate, which again, at the conclusion of the reaction, if we treat that with water, it generates the aromatic carboxylic acid. So this becomes a useful way to generate benzoic acids in synthesis. And just an example here is using this trimethyl benzene structure, where we can take this aryl bromide, treat that with magnesium to give the Grignard. Addition of carbon dioxide to that reaction mixture then generates the carboxylate salt, which on workup gives this sterically hindered carboxylic acid. Because carboxylic acids are important building blocks, in particular with sort of drug discovery, because amides are quite prevalent in drug discovery, and you can use carboxylic acids to generate a number of amide functional groups. Grignards will also react with epoxides. So here I've just shown the simplest epoxide, oxirane, reacting with N-butyl magnesium bromide. And in this instance, you have the Grignard adding to one end of the epoxide and opening up the three-membered ring. So it releases a lot of strain to give your alcohol product. And so the mechanism is just shown at the bottom here. So in this mechanism, we have a epoxide with a single carbon substituent. And we can see that the Grignard actually attacks from the least substituted end of that epoxide. So we get good regio control using this chemistry to generate, again, our alkoxide magnesium salt, which we get back as the alcohol after we add water or acid to that reaction mixture. And again, that regio-specific nature of this reaction can be exploited in more complex systems. For example, here with this cyclohexyl epoxide. And in this instance, you can see that the tertiary butyl group on one end of this cyclohexane ring actually prevents attack of the Grignard to one end of this epoxide, and we get selective opening of the epoxide at this less sterically hindered end to give us our cyclohexane alcohol. Nitriles are another similar reaction mechanism, or undergo similar reactions as carbonyl compounds, as they can be considered as a carbonyl-like compound. And we can use these as a good way to make nitriles to make ketones from Grignard reactions, which, as we discussed in the previous slide, the ketones are quite reactive with Grignard, so they're actually quite difficult to stop the reaction at that point. But what happens with a nitrile is that we get attack at the carbonyl end of the nitrile. In this addition reaction, the electrons then move up to the nitrogen to give the anionic nitrogen species, which forms a somewhat stable interaction with magnesium salt in solution. And therefore, that makes that a little bit more resistant to addition of the second Grignards, addition of a second Grignard. So then when we quench this reaction with water or acid, we can actually stop the reaction at this synthetically useful ketone compound. And here's just an example here where we've taken a benzonitrile, treated that with ethyl magnesium bromide to generate this unsymmetrical ketone compound. Another way that we can stop the Grignards reacting with or further with ketones is to use something called a wine Rib Amide. So first, I'll just discuss what a wine Rib Amide is. It's just shown on the right here. So this is an amide that has also a tertiary amide where one of the substituents is a methoxy group on the nitrogen. And the reasons for this will become apparent later. But these are easily generated from carboxylic acids. So we can convert the carboxylic acid to acid chloride using something like thionyl chloride or oxalyl chloride. This then reacts with this hydroxylamine-like compound to form the wine red amide, which is then what we use in our Grignard reaction. So when we treat this wine Rib amide with our Grignard reagent, we end up getting this ketone or this unsymmetrical ketone product. And this wine Rib amide works by basically stopping the reaction after the addition for the first addition. So in this case, we are looking at a methyl magnesium Grignard or methyl Grignard. And you'll note we're using 3 equivalents here, which should be normally more than enough to take this down to an alcohol. And it's also at 0 degrees, which is a lot warmer than some of the other reactions that we've encountered. But what happens when we add the carbon to the other methyl Grignard to the carbon end of the carbonyl is we actually generate this intermediate here where the magnesium ion is chelated by both the alkoxide that we've just generated from the euthyphilic attack and also the oxygen of this methoxy substituent here. And this is a nice stable 5-membered ring, which is happy to sit in solution until you add your water to the reaction and generate your ketone. So because this intermediate is stable, we don't get reformation of the carbonyl bond and we don't kick out this hydroxylamine component during the reaction. And because of that, we're able to generate our desired ketone. So now I sort of want to get into organolithiums in a little bit more detail. And what I'm hoping to do through these next slides is just highlight how synthetically useful these reagents can be and how we can get a lot of different selectivity in synthesis. And this is just a snapshot of reactions that are available to us using organolithiums. So one thing that's important, we've spoken about sort of halogen metal exchange before. Here we're talking about lithium halogen exchange. So we can use commercially available organolithiums to swap your lithium with your alkyl iodide. So in this reaction, we can see that we can generate this carbocyclic system with the lithium bound to the carbon skeleton. So we've just had this swap of the lithium shown in red with the iodine. And then we've also generated this tertiary butyl alkyl iodide. And this alkyl iodide is actually quite reactive to organolithiums itself. So if we were to just use one equivalent of this alkyl lithium, when we generate this alkyl iodide, it can actually then go back and react with our reagent. So the number of equivalents we add to a reaction is actually quite important to the successful outcome of these reactions. So what happens here is that your generated alkyl iodide reacts with another molecule of your organolithium to actually eliminate hydrogen iodide to form this alkene. So by using 2 equivalents of the alkyl lithium, we're actually able to fully convert this alkyl iodide into this organolithium compound by consuming byproducts of this reaction. Another useful feature of organolithiums is that the lithium coordinates strongly to oxygen typically, or groups that have a lone pair to donate. And this is quite useful for a process called orthodirected methylation. And in this case, we're deprotonating an aromatic ring, such as this benzene shown with an arbitrary directing group here. And what this directing group does is it'll actually coordinate to the lithium of the alkyl lithium and direct that to deprotonate at the proton in the ortho position. So that's hence the name orthodirected methylation. And that can give us our organolithium compound here. And just to highlight the utility of this, we can actually show one example of an electrophile this organolithium reacts with. In this case, we've got molecular bromine. So in this case, the lithium will attack, the organolithium will attack at the bromine to generate this aryl bromine species. And the reason I wanted to highlight this one is because we've actually now used the basicity of the organolithium to generate this aryl bromine compound, which is also something that we would have used as a starting material to generate other organolithium reagents. So you can actually sort of get the reverse, almost the reverse process of your halide reduction reaction happening. And so these directing groups can take the form of, as I said before, just about anything with a lone pair, so such as amides, sulfonamides, ethers, halogens, and the list is quite extensive. And the electrophiles we can use here are things like halides, which I've shown with bromine in the top line, carbonyl groups, which is similar chemistry to what we just showed with Grignards. We've also discussed transmetallation, so we can actually add other metals in that position. Some alkyl halides will also react in this way, as well as phosphorus and sulfur compounds. So you should hopefully be able to start to see how powerful this lithiation chemistry can be. We can also get selective functionalization of different halides within the one molecule. And this is often controlled by the stoichiometry of the reagents that we add. So in this case, we are looking at this dibromobenzene compound. We add two equivalents of bromolithium, the first to undergo an exchange reaction, the second to mop up the butane bromide that was formed. We can actually selectively swap out one of the bromine atoms with a lithium to generate this organolithium intermediate. And then using chemistry that we discussed before, we can quench this with carbon dioxide, for instance, and generate a compound like this benzoic acid. Another example is just shown at the bottom here, where it's actually the difference in reactivity of the halide, which dictates the regioselectivity of the reaction. So in this first step, we can see that we've just taken our organolithium and done a halogen metal exchange with the bromo connected to the aromatic ring to give this organolithium intermediate. And this reaction works because this halogen metal exchange does not work very well for alkyl chlorides. So this carbon chlorine bond is untouched. And then this reaction, so this example, it can actually be used in two ways. If we just take this intermediate organolithium and just allow it to warm up, it undergoes the nucleophilic substitution at the carbon adjacent to the chlorine to give this cyclobutane compound. If, however, we treat the organolithium with a benzonitrile or another electrophile, the organolithium can add to the carbon end of the nitrile to generate this intermediate, where we've now got the negative charge on the nitrogen. That is in close proximity to the delta positive charge on the alkyl halide, and this can actually react to form this cyclized product on the right here. So we can start to see how, depending on the choice of our reagents and our substrates, we can actually affect different chemistries and in a regioselective manner. Excuse me. Another process that organolithiums can go is called carbolithiation. And this is where your alkyl lithium can add across a pi bond, which can be an alkene or an alkyne. And this is largely dictated by the reaction temperature. So in the example shown below, we have this aryl bromide species with this tethered alkene coming off the bottom. And if we do the halogen metal exchange with butyl lithium, we can generate this intermediate lithium species. If we follow this across the top and raise the temperature of this reaction to 23 degrees, or just ambient temperature, that lithium carbanion can actually add across that double bond to form this cyclic species, with the lithium at the terminal end of this, on the external end of this ring. And then we can quench that, shown here with just D2O, to give the cycloalkyl product. So you can see here, this is quite a good reaction, gives 92% after 1 hour if we allow the reaction to warm to room temperature. If we go back to this intermediate shown in the middle top, if we were to just take this, keep it at low temperature and add D2O to it, we would actually incorporate the deuterium atom on the aromatic ring. And if we keep the temperature at -78 after 2 hours, this becomes our exclusive product. So now you can sort of see that the temperature with organolithiums can start to dictate some of the selectivity that you might obtain. Also just wanted to quickly point out that this is also, I've shown here using deuterium oxide. This is a good way to introduce deuterium into structures which have implications in drug design and also studies of reaction kinetics. We can also use different organolithium reagents to give selective outcomes based on whether these reactions undergo lithium halogen exchange or LDA. So what I've shown on this slide is in the middle, we've got 3 different starting materials. On the left, we're treating these with butyl lithium to give the halogen metal exchange product. And on the right, we treat these with LDA. This is the amine base that I showed earlier to deprotonate part of that ring. So depending on the choice of your organolithium, you can actually see that we can convert this bromothiaphene compound to an organolithium with the lithium in the 2 position of the thiophene ring, and we've lost the bromine in this instance. However, we've used something that's more basic, or basic but not nucleophilic, we can actually deprotonate the other side of that thiophene ring. So depending on the choice of reagent, we can actually get very different intermediates and then very different chemistry. Similarly, we have this dibromothiaphene shown in the middle here. Treat that with butyl lithium. We can generate our lithium organometallic, but still have a bromine on the other side of the molecule. If we use LDA, we can actually deprotonate a different position of that aromatic ring. And a similar example is shown here where we use butyl lithium as a base in this instance using a thiophene carboxylic acid. The first deprotonation occurs at the carboxylic acid, which is quite acidic. And then the second deprotonation using butyl lithium occurs adjacent to the carboxylic acid. Whereas if we use LDA, we deprotonate the carboxylic acid first, but then the next step is deprotonation of the CH at the other side of the ring. So hopefully I've just sort of been able to show that organolithiums, depending on your choice of organolithium, your choice of substrate, temperature control, stoichiometry control, you can generate a diverse amount of intermediates in chemistry, often from similar building blocks. So they're quite powerful tools. And so lastly, just wanted to quickly cover organocuprates, which are an alternative to Grignard chemistry. So as we discussed before, typically with a Grignard reaction, here we've got a unsaturated ketone compound. Typical Grignard reactivity is to add to the carbon end of the carbonyl group. It's shown here. So this is what we call a 1,2 addition product. It's adding to the 1 being the oxygen, 2 being the carbon position of the carbonyl. if we convert an organometallic or Grignard or an organolithium to an organocuprate species, these are often considered to be a much softer nucleophile, which in the context of this enone intermediate means that they'll actually add to the carbon end of the alkene, shown here on the right. So this is just what we call a 1,4 addition product, or also known as a Michael product. So in general, organocuprates have different reactivity or to Grignards and organolithiums. So they have slightly reduced reactivity. They are softer nucleophiles, which means they will react to different functional groups. For instance, they won't react with ketones, aldehydes, esters or amides, which Grignards will, but they will react with epoxides, alkyl halides, aryl halides, and acyl halides. So they offer differences in reaction outcomes and selectivity as the other organometallics. And this is just the classic Gilman reagent. This is just the generation of an organocopper species from methyllithium, shown here in this top arrow, where we treat methyllithium with copper iodide, and that generates this dimethyl copper lithium reagent, which is called a Gilman reagent. And again, this is used for this 1,4 addition chemistry. And some of the other examples that I mentioned in the previous slides that you can achieve with Gilman reactions is converting the aryl iodides to methylate or alkylate aromatic rings. You can also substitute alkenyl halides to generate the substituted alkene. They can undergo substitutions, nucleophilic type substitutions with electrophiles, shown here this allylic type substitution, ring open epoxides, and also add to acid chlorides to generate ketones. So quite a powerful alternative. Yeah, so that's just the end of the organometallic section. So next, I just wanted to start to talk about some carbonyl chemistry. So our carbonyl groups, which we counted in just the recent section, we're showing that they can act as electrophiles reacting with organometallic reagents, but their reactivity extends beyond that. As we'll see shortly, carbonyl group compounds can be both electrophilic and nucleophilic, depending on their substitutions. And in this section, we just want to cover the structure and reactivity of carbonyl compounds, ways that we can synthesize carbon-carbon double bonds, and we're just going to touch on some rearrangement reactions. So hopefully after we've gone through this section, should understand the diverse reactivity of carbonyl compounds, learn how to prepare carbon-carbon double bonds, and also be aware that carbon-carbon bond can be formed in rearrangement reactions. So there's quite a few sort of well-known named type reactions in carbonyl chemistry. So this is just a list of what we're going to cover first. I won't go through that list in the interest of time, but we'll encounter them shortly. So one useful reactivity of these ketones, for instance, is if we have a alpha proton. So when we talk about alpha, we're talking about the carbon position which is adjacent to the carbonyl carbon. Again, this is this LDA base. We can actually deprotonate that position and substitute it with an electrophile. So in this instance, the electrophile is bromine again, and this can generate alkyl bromide compounds like this. So mechanistically, this happens as the base can deprotonate the proton in the alpha position. Again, we don't typically think of carbon-hydrogen bonds as being particularly acidic, but in this instance, the electrons can delocalize to form a double bond in between the two carbons and push the electrons onto the oxygen to give an enolate intermediate. And because there's resonance stability to that intermediate, it's more stable, and that's why it becomes acidic. And we're just showing that in one form here. Now, in this form, we've got the negative charge on the carbon, which is what typically reactive species, or how we determine where it will react. In this case, it then attacks one end of the bromine to kick out a bromide anion to generate this alpha halo ketone species. We can also do this under acidic conditions. So under acidic conditions, we have, we're showing here in this, this scheme, where we have this generic ketone. Under acidic conditions, the proton adds to the oxygen end of the carbonyl group and causes a tautomerization to give this sort of alkene or enol intermediate. This enol intermediate is in resonance with this species. And again, we have our reactive electrons on this alpha position of the alpha carbonyl, which can react with electrophiles, and then the solvent can pick up this proton, which is used to catalyze the reaction, and we can generate our alpha substituted product. The top reaction can also be done under acidic conditions in this way, where we can take bromine in the presence of acetic acid to form these alpha bromo ketone type products. So here we're just reiterating this acidity of the alpha proton, just showing what we showed in the previous slides, how we can deprotonate this alpha position to give this enolate intermediate. That's the most stable form of this compound. If we draw it in this resonance form, it's the most, it shows us how it will react. And in this instance, again, we're just reacting with a generic electrophile to generate this alpha substituted type product. And what we know as well is that carbonyl groups can also act as electrophiles. So if you are able to generate this reactive alpha anionic type enolate compound in the presence of another molecule of your ketone, it can actually react with itself or react with another molecule of itself to generate this beta hydroxy carbonyl compound. And this reaction is actually known as an Aldol reaction. Sorry, that's because the product is known as an aldol, so it's known as an Aldol reaction. So this is just a snapshot of the reactions you can do by functionalizing the alpha position. And also, if you, depending on what reagents you use, if you use here we've got a TMS chloride, which is a trimethyl silyl chloride. The silane, it's got a silicon atom which is quite oxyphilic, so we can actually generate this TMS enol ether, which can be used in further chemistry. We can generate this enolate, so we can trap that with methyl iodide to generate alpha methyl carbonyl compounds. We can react this with aldehydes to generate aldol reaction products. We can react that with these enone compounds to generate Michael addition products. If we have a peroxide or similar reagent, we can add oxygen to that position in the form of an alcohol. And as we saw in previous slides, we can also add halogens into that position. So we briefly touched on the dimerization reactions before, which was an aldol reaction. That's all well and good if that's the product you're trying to make, but what about if you're trying to make some of the products in the previous slide where you don't want that dimerization? You have to be able to prevent that dimerization. And one way we do that is to get complete enolization. And to do this, we typically use one equivalent of a strong base so that all the molecules are enolized first before they can react. And we do this at low temperature, again, to prevent any reactivity between the intermediates as they form and starting material which remains in solution. So here is just a reaction showing that. Once again, we're looking at this lithium diisopropyl amide base, LDA, in THF at temperatures of -78 degrees. We can get complete conversion to the enolates, and we can prevent that dimerization product. And so again, just reiterating, the starting material can react with itself, but if we use low temperatures, we can prevent this from occurring. And then we can, by using a stepwise introduction of reagents, we can generate our enolates, then add in our second carbonyl compound. And as a result, we can generate mixed aldol products without the complications of the starting material reacting with itself. So depending on the addition of reagents and the temperature control, we can form aldol products or mixed aldol products, depending on what we want to prepare. Another way we can get selectivity is if our enol is asymmetric. So here we have a lactam ring, which can only deprotonate on one alpha position. And we can use this chemistry to generate this alpha methyl product. The same goes if we've got an alpha position that then has aromatic ring here. We can generate a stable anion, which can also be used to quench with another electrophile to generate this sort of alpha methyl type compounds. If we have an unsymmetrical ketone shown here on the left, it's actually possible to shift the reactivity between the two positions. As you can imagine, if there was no control of this reaction, you might get addition at this alpha position, or you might get addition to the alpha position on the other side of the ring. So to do this, we can put the reaction under kinetic control, which is what we've just been speaking about, using something like LDA at minus 78 degrees. This takes the most accessible proton, which is on the least hindered side, to generate our enolate. If we keep the temperature low and add our electrophile in, we can then get reaction at one specific, less substituted alpha position. If we use a weaker base with an oxophilic electrophile like this TMS chloride that we touched upon earlier, at room temperature, what we can find is that we'll form the most thermodynamic product, so the most stable product. And that's with here showing with the more substituted alkene is the more stable. So if we do that reaction, give it time to equilibrate, the alkene will form on the opposite side, which can then be trapped with your electrophile to give the opposite regioselectivity for our chemistry. So this is important for things like mixed aldol reactions. So if you appreciate here, we've just got a proposed reaction where we've got two aldehydes, one with a 2-carbon chain, one with a 3-carbon chain. If we were to just mix these up with the base to catalyze the reaction, we could get up to 4 different combinations of products. And depending on what electrophile we use to trap it with, we could get, for some, 2 enantiomers, so on the left here or the right, or we can get multiple diastereomers. So you can end up with quite a complex reaction mixture, which isn't actually very useful in terms of preparing our desired compound. However, if we perform this reaction where one of our electrophiles does not contain an alpha proton, we can actually get a clean aldol reaction. And an example we've shown here is when we use something like a benzaldehyde shown in the top row or formaldehyde on the bottom row. So we can generate our enolize our ketone, add our aldehyde to that reaction and get our desired aldol product. So that works very well for aldehydes. And then also these aldol products can actually further react to dehydrate to give alkenes. Another way we can control this reaction is if one of our alpha or compounds with an alpha proton is much more acidic than the other. So in this case here, we've got this dicarbonyl compound. So because we've got 2 carbonyl groups adjacent to this position, that means there's more resonance structures, meaning it's a more stable conjugate base, which means the pKa is much lower. So in this instance, it's around about 9, whereas here we've just got our ketone, which has a pKa of about 19. So if we use these 2 substrates, for instance, we can use a much weaker base like sodium methoxide shown here, which has a pKa of around 16. What that means is that actually won't enolize this ketone component of the reaction, but it will readily deprotonate the alpha protons in between these carbonyl groups. And as a result, we can generate this top product as the major product, whereas we may get a tiny amount of this minor isomer. And so we've just got some examples of different pKa's of alpha carbonyls here, just showing that depending on your choice, you can actually reliably predict the reaction outcomes based on the pKa. Using this chemistry, we can also generate enones, and this is because the product we generate still has an additional alpha proton, which in the presence of a base used in the reaction is that it can still be deprotonated after you get electrophile addition to that position. And so if that's then removed, you can then eliminate the OH to give this dehydration product. So one of the ways that we can drive that is to use an excess of base just to ensure that that process happens, but also we can heat the reaction to drive off that dehydration product. So that's another way that's a way we can generate enones using this chemistry. And that's just shown in this mechanism here where we're depicting the deprotonation of this alpha proton, which is between our carbonyl and our alcohol group. It enolizes this carbonyl group to give the enolate. This enolate will then collapse down, pushing electrons through, forming the alkene in this newly formed carbon bond and causing hydroxide to leave as the leaving group. And that generates our enone product. And we can just see a few examples here where we've got a variety of different alpha acidic carbonyl compounds shown on the left. All of these, you'll notice, have two electron withdrawing groups adjacent to the alpha carbon, which means that it can be performed using sodium methoxide and can be selectively reacted with the carbonyl of choice to give these enone type compounds, which can be used with further chemistry, including things like the Gilman reagents, which we showed before. Excuse me. Another way we can utilize this improved acidity of these beta dicarbonyl compounds is in the malonic acid synthesis or the acetoacetic ester synthesis. So in this process, what happens is that we get deprotonation to this alpha position. Again, we can use a base like sodium methoxide because we've got the dual activating role to generate this enol, which is resonance stabilized, and that can react with electrophiles such as an alkyl halide to add a carbon in between this position. So we can then take that alkylated intermediate and treat that with sodium hydroxide, which cleaves off both our ester groups to give this carboxylic acid intermediate. If we then treat that with acid and heat, we can actually affect decarboxylation of one of those carbonyl groups. And that leads to the loss of carbon dioxide, and the resultant product is this new carboxylic acid. So using this chemistry, we can take these beta dicarbonyl compounds, as long as one is an ester or an acid, we can alkylate in that alpha position, or the net reaction is alkylation in the alpha position. So if we've got this compound here is melodic ester, we can use that to generate these sort of substituted carboxylic acids. If we use acetoacetic ester, shown here on the left, you'll notice that one of our alpha carbons is now a ketone rather than a ester. We can use the same process to generate substituted or alpha substituted carbonyl compounds. These reactions can also happen intramolecularly. Sorry, there's a cat jumping on my desk. And we can use that as a powerful way to introduce new ring systems in our molecules. So just shown here are a couple of examples where we've taken this beta dicarbonyl compound treated with sodium methoxide to generate this cyclic enone. Similarly, we got this diketone compound can be converted to another enone-like compound. And again, we can form a 5-membered ring from this dicarbonyl compound. So looking at this bottom example, we can see this is quite, you can predict quite readily what products you might form from this reaction. So we've shown two potential pathways here, because as you could appreciate, each carbonyl group actually has two alpha protons. So depending on which alpha proton leads to enol formation will potentially lead to different outcomes of the reaction. So just shown here by this arrow in A, if it's the internal alpha proton which is deprotonated, if we draw a mechanism out where that reacts with the carbonyl group, we actually form this three-membered ring. This is actually not a very energetically favourable process because that ring is quite strained and it's more likely to fall, to pop back open to give you enolate than to progress any further in the reaction. Also, the elimination of water is highly unlikely from this product, as the alkene is quite strained and unlikely to form. So what happens in reality with this is that we get a enolization to this terminal end of the ketone that then reacts with the adjacent carbonyl group to form this five-membered ring. And now we've got a more stable, happy ring system, which can then undergo the dehydration, and we can generate these strain-free cyclopentyl rings. Another quite useful reaction is the Glycine Condensation, and this can be used to dimerize different esters to form beta carbonyl ester compounds, as shown here by this reaction. So just looking at this first example, we'll just go into the mechanism next about how this actually occurs. So we have just shown here, we've got two equivalents of your starting material shown next to each other. For one equivalent of the starting material, we form the enolate through the action of base, shown here by these arrows, to generate this reactive alpha carbonyl intermediate. This can then react with the ester carbon of your additional starting material, which just undergoes the normal nucleophilic acyl substitution type reaction. So we push the electrons up onto the carbonyl oxygen, and that can then collapse down to give sodium ethoxide, which regenerates your reagent in this case and gives you that beta dicarbonyl compound. Again, if we can do the mixed Clies and condensation, provided only one of your reagents has an alpha proton. And that's just shown by this example where we've got this benzoic acid ester. So this has no alpha proton, is not enolizable. And whereas you've got your other component which has the alpha proton, so you'll generate your nucleophile from this, and your benzoic acid ester will act as the electrophile in this mechanism. Additionally, we can also block different positions of the alpha, or block different alpha positions. That's with further substitution. So for instance, here we have a ketone with a dimethyl on one alpha position. So obviously there's no alpha protons for deprotonation on that side. And also the ester has this trimethyl sort of substitution here, which means it has no alpha protons. So choosing the right reagents will also enable you to dictate which product is formed from this reaction. We can perform the intramolecular, the Clies condensation in an intramolecular fashion as well, and this reaction is known as the Dichmann Cyclization. And in this case, we can take diester compounds, treat those with a base like sodium ethoxide, that undergoes the same mechanism on the previous slide to generate these cyclized compounds. And just an example of the mechanism shown here, where we deprotonate this alpha proton to give this reactive intermediate, which then attacks the adjacent carbonyl group in a nucleophilic acyl substitution mechanism to give this carbonyl group. And this reaction is then has another alpha proton generated here, which can react with the base in the reaction. But that is now quite a stable anion, and it'll actually sort of sit happily in solution until you finish the reaction with the addition of water or acid. So this becomes another way to reliably generate rings. And this, now some we've spoken about generating enones. We've also spoken about Gilman reactions and how they react in a 1,4 addition manner. So this is just a little bit more on that reaction. That reaction is known as the Michael reaction. It's also called conjugate addition, as well as that 1,4 addition that we mentioned earlier. So in this process, we have enone type compound. So we have this alkene, which is conjugated by resonance to this carbonyl group, which is why it's also known as conjugate addition. And that can be attacked at the 4 position of that structure or at the terminal end of that alkene to substitute at the end of that alkene to generate ketone products. And so in the case of carbonyl chemistry, we can use enolates that we've just been discussing to react with these alpha-beta unsaturated systems. So that's just shown here in this one example. We've got this acetic acid ester, which we saw before, can deprotonate and react with the terminal end of that alkene to generate more complicated carbonyl compounds. And the mechanism follows this pathway shown down the bottom. So as shown before, we can use base to deprotonate the alpha proton to give our reactive intermediate. This reactive intermediate then attacks at the end of the alkene. The electrons from the alkene then form enol by pushing up towards the carbonyl group, and then the carbonyl electrons go up onto the oxygen to give this enol intermediate, which again, with the action of water or acid, we can quench to form our desired product. And so this Michael acceptors in this reaction, so these are the conjugated components, can take the form of aldehydes, esters, ketones, nitriles, and also alkene nitrates, which means it's got quite a diverse range of compounds you can prepare for this. And again, got our Michael donors are more of these alpha-beta unsaturated ketone type compounds. Another impressive application of this sort of chemistry is known as the Robinson annulation. And here it's the sequential combination of the Michael addition reaction and an Aldol reaction. And it occurs between an alpha-beta unsaturated ketone, shown on the left, and a beta keto or a beta diketo compound, like one shown here on the right. What happens in this reaction is we get this Michael addition occurring in the first step, which we covered in the last slide. Then with this ketone in our Michael sort of portion of the molecule, we can generate an enolizable or deprotonate the alpha position of that ketone that can then react with the carbonyl of your aceto acid component from your original reactants to generate the aldol product in the presence of base. That aldol product can then undergo the dehydration to give this enone, this cyclized enone product. So we've got 2 quite simple substrates here. Just the treatment of base undergoes a cascade reaction to develop this or to prepare this, advanced ring compound, which can be used for further chemistries. All right, so this is just an overview of what we covered. I probably won't go over that in the interest of time, just to get on to sort of the next chemistry, where we're going to look at some more formation of double bonds. So we've just covered some carbonyl condensation reactions, but now we just want to look at some chemistry where we can convert carbonyl groups to alkenes. And this is typically referred to as olefination chemistry, olefin being the sort of old description of old name for an alkene. So one famous example of this is the Wittig reaction. If you remember back to one of the first slides, this was also responsible for the awarding of the Nobel Prize as well. Here we are converting a carbonyl compound, which is shown on the left here, to an alkene. Sorry, just didn't update the name of that. It should say alkene under that. Using a phosphorus ylide compound, which is shown in red. So we can see from this reaction that we've got an anionic carbon at one end of this phosphorus ylide, and that ends up replacing the oxygen of your original carbonyl compound to form this alkene. But the interesting thing about this example is that our alkene is now outside the ring, whereas before we've been looking at alkenes that are inside the ring. So these ilids look like rather complicated molecules at first, but they're actually quite easy to prepare. They're typically prepared from an alkyl halide. They react with triphenylphosphine. So normally we get attack of the lone pair on that triphenylphosphine at the carbon end of that alkyl halide bond to displace the halide to form our carbon phosphorus bond. Then in the presence of base, we can deprotonate. This is now effectively, you can think of that as an alpha proton that we've just been discussing. You can deprotonate this to give this ilid structure. This ilid structure is stabilized by the fact that it has this phosphorane resonance structure. So this allows us to reliably produce this reactive intermediate. Now the mechanism of this reaction follows typical 1,2 addition sort of carbonyl chemistry that we've seen before. So here we have our phosphorus illid attacking a benzaldehyde compound. So the carbanion end of this compound can react with carbon end of the carbonyl group, while the electrons from the double bond, instead of going up to the oxygen, tend to go towards the phosphorus to generate this oxyphosphatane intermediate with this strained 4-membered ring. Then we get collapsing of that 4-membered ring to give our alkene product and also this triphenylphosphate oxide. And the main driving force for this reaction is actually the strength of the phosphorus oxygen bond. It's actually a very strong bond, highly energetic. So the formation of that bond is favored, which drives the reaction through this strained intermediate to give the alkene. So this Wittig reaction is Z selective. So Z being trans geometry of the alkene. So if you take an illid like shown here, react that with your aldehyde, you will get this trans geometry of your alkene. Alternatively, if you generate an illid with further stabilization, adjacent to the carbanion, so this is sort of similar to our alpha carbonyl type stabilization, then we'll actually generate our cis alkene shown here. So depending on your choice of illid, you can actually generate different isomers of double bond. Another modification to the Wittig reaction is called the Horner-Wadsworth-Emmons, or just HWE reaction. This is another Z selective olefination, and that comes about because you've got the additional stabilization, this ester group. It can also be used to make alkenes, reacting with aldehydes and carbonyl compounds, but it has different advantages, or has advantages versus the Wittig olefination. So the phosphonate stabilized ilids are more nucleophilic than the Wittig ilids, but they are less basic. So that just means you need a stronger base. So here we've got something like sodium hydride, but one of the main advantages is the byproducts that are performed from this reaction are actually water soluble. So that makes the workup and isolation of the products much easier because you can do an extraction between organic solvent and water just to remove the byproducts of that reaction. And just quickly, there's also other modified versions of these reactions. For instance, we can use sulfone compounds here, just showing a Julia olefination. As you can see here, it's a rather steppy reaction involving our friends at organometallic base to generate alkenes over a number of steps. We can also use these other sulfone-like compounds, again with another inorganic base here to generate E-selective alkenes. And there's also a reagent called TEB reagent, which is shown here, which is a titanium alkylidine compound, which just means you've got the titanium with a double bond to a CH2. This is similar to the Wittig reaction in that you can convert ketones like shown here to this exocyclic double bond. And this is driven by the fact that titanium forms very strong bonds to oxygen. And this is also quite good because you can take aldehydes and convert these to alkenes. It also works with ketones to alkenes, but you can also convert esters to enol ethers and amides to enamine type products. So another thing I might quickly touch on is a type of carbon-carbon bond formation that we can generate from rearranging of products. So this first one here is the first known example of this type of reaction called the Clies and Rearrangement. It was the first sigmatropic rearrangement to be discovered all the way back in 1912. So when we talk about the sigmatropic rearrangement, essentially just the thing to remember for this course is that we are moving one of the sigma bonds in the substrate to another position, sort of shown here in red. That's the overall outcome of that reaction. So the first one discovered was this rearrangement of an aryl ether to give this ortho-alphenol product with the new carbon-carbon bond shown in red. This is a reaction that all happens in one step. So it's a concerted mechanism where we just get a rearrangement of electrons shown here. So we have our alkene sort of attacking this ortho position of the aromatic ring. This pushes electrons up to the oxygen to form a carbonyl, and that breaks this other carbon-oxygen bond to reform an alkene at the other end of this allyl group. This is usually performed in heat, and in the case of this originally discovered reaction, we actually generate this really unstable phenol tautomer of an aromatic ring. So this rapidly tautomerizes to give this allylated phenol compound. So that's very useful in generating alkenes on aromatic rings. But if this intermediate actually is also, well, it's not useful in this context, it's useful in aliphatic systems. If we don't have this unstable phenol tautomer, we can actually use this reaction to take an allyl vinyl ether, shown here, to convert to this unsaturated carbonyl-like compound. And you can sort of appreciate that we've just been talking about Michael acceptors and that sort of thing and generating enones. This is a way of generating alkene-containing carbonyl compounds, but with additional atoms in between your alkene. So homologated versions of your enone type compounds. I probably won't go into this too much detail. I might just in the interest of time, but just here we're just quickly showing that allyl vinyl ethers can be prepared from the condensation of an acetal, shown here, and an allyl alcohol, which is shown sort of towards the right here. Just under acid catalyzed conditions, we can generate these reactive intermediates to form our allyl ethers. And if we perform this reaction in the presence of heat and acid, we can just then convert this allyl vinyl ether in one step to the unsaturated aldehyde. So we can generate these enone type compounds just by heating an allyl alcohol with an aldehyde, an acetal, in the presence of acid. And this chemistry can be expanded to ketals as well. So here we've got a carbon, 2 carbon groups on this ketone. That gives us our ketone product shown at the right. Variation of this reaction is called the Johnson-Claisen reaction or rearrangement. If we use an ortho ester, we can generate ester products shown at the right, all going by the same mechanism. And if we use an ortho amide, this is known as an Eschenmoser Claisen reaction, we can actually generate amides with alkenes tethered to them. So depending on our starting material, we can generate a vast array of products. Other variations to this chemistry is the Cope rearrangement. So it's just the very basic Cope rearrangement shown here with the same arrows as we showed for Claisen. What you might appreciate is that the starting material for this particular reaction is the same as the product. So there's actually no real reaction taking place, but it's just showing that this sigma bond can be moved as well as the alkenes moving. So that can be applied to more complex systems as a powerful way of manipulating the structure. This type of alcohol can be undergo an oxycoat reaction. So if you use a hydride base to deprotonate this alcohol, you can generate this intermediate, which is similar to what we saw for the Clies and Rearrangement. Heat that, you can lead to the same shifting of the sigma bond to generate this enolate intermediate, which treated with acid gives you a way to access aldehydes with alkenes attached, separated by sort of 3 additional carbons. And we can also use this process to generate acids with alkenes tethered, and that's the island Clies and Rearrangement. Here we'll take this allylic alcohol and convert the oxygen into an ester, shown here. This ester has an enolizable alpha proton, which can be deprotonated by LDA to generate this intermediate, which the application of heat and then quenching the reaction with water or acid can be used to generate these carboxylic acids. And so that is sort of what I have for the first section of this talk. So what I might do, Rani, if that's all right, is just take a couple of minutes to get a drink and then come back. Does that work?
Yeah, it's okay.
Yeah,
it's okay, Tran. Yes, yeah.
Yeah, and then I'll coming back with some organometallic chemistry for the next one. So
so we can like put the discussion session after you finish. After you finish.
Yeah, that would be best, I think.
Okay. Yeah. Okay. So if you want to take a break, you can have 1 or 2 minutes, for the break.
Yeah, a couple of minutes will be fine.
Yeah, a couple of minutes, yes.
Yep.
Yeah.
All right.
Before Dr. Tran will continue the lecture.
All right. Thank you. back.
Back.
Yeah,
You can
also
start again.
just in the interest of time, I just had to cut a couple of slides out of the next bit as well.
All right.
So hopefully we can leave some time for questions. So
Yeah.
Yep. Happy for me to start?
Yeah, we can.
Right.
You can.
I hope no one's run off and not come back. All right. So in this section, I wanted to look at some of the more modern chemistry, or chemistry that has really sort of revolutionized organic synthesis. And a lot of that chemistry has been made possible by the use of transition metal catalyzed reactions.
Yeah.
So, simplest terms, when we talk about transition metal catalyzed cross-coupling in terms of carbon-carbon bond formation, it is just the controlled synthesis of carbon-carbon bonds using aryl halides and an organometallic component in the presence of a transition metal. And these advances have, in recent years, have made it possible to undertake reactions which would be previously challenging or previously impossible, and make these occur quite easily. And another benefit of using transition metals and catalysis is that it lowers the energy barriers in reactions, which means they can be occur at lower temperatures and have greater synthetic utility. So the oldest example of a transition metal catalyzed reaction I've shown in this slide is the Ullmann reaction. And this was actually discovered or reported back in 1901. So it's been around for a long time. So the Ullmann reaction typically would take an aryl halide compound where the halide was either bromine or chlorine, and in the presence of stoichiometric amounts of copper and high temperature, you could generate these biaryl compounds. So we got two aromatic rings joined with a single bond. And at the time, this was the only real reaction to do this, but it did come with its own issues. So it often requires temperatures of 100 to 300 degrees to get the reaction to occur. High temperatures like that are typically incompatible with a lot of different substrates and can lead to decomposition of reagents and things like that. So your reagents you use in your reaction might decompose before you get a successful reaction. So the higher temperatures required for this reaction was a limiting factor. Additionally, the yields for this type of chemistry were sporadic. They weren't consistent and reproducible, which really limited the synthetic utility of this process. If you think about, if a drug company was making a particular drug that used that chemistry, they need to be able to reliably generate compounds with the same yield each time they prepare this compound so that they can prepare their drug, for instance. And this chemistry was limited to dimerization. So you had the same aryl halide could form this symmetrical product. So you couldn't use, say, a different alkyl halide to give a non-symmetrical system. So it was very limited to producing only symmetrical biaryl compounds. So for this section, well, say here, I just cut out some slides on the history of transition metal coupling, so that it's just going to take a bit too much time, but I want to introduce sort of an overview of the reaction mechanisms of transition metal catalyzed cross-coupling and introduce some of these reactions which have revolutionized organic chemistry and introduced a whole lot of new possible reactions and also compounds that can be prepared. I'm going to discuss these in the context of palladium, as this is the most widely used metal for these processes. But it's important to note that there are other common metals which can be used, such as nickel, copper, things like rhenium, rhodium, ruthenium, iron, etc. So hopefully after this section, you'll have a better understanding of the impact that transitional metal catalyzed cross-coupling reactions has had in the formation of carbon-carbon bonds, you'll have an understanding of the general catalytic cycle and some of the processes involved, and also understand some of the common reactions out there. And also just be aware of the multitude of reactions that are now at the disposal of organic chemists. So in general, we can represent a carbon-carbon bond cross-coupling reaction, just sort of shown here. On the green box on the left, we have our aryl halide component. And so X, just again, representing a general halide. We can have a variety of different halides just shown here. I'll go into these in a little bit more detail later. And we normally react that with some sort of organometallic. So again, just highlighting the importance of organometallics again as they make this sort of chemistry possible. You will usually have some sort of catalyst. Typically there'll be a base involved, and obviously this will be performed in some sort of solvent with the application of heat, and the outcome should be some sort of controlled synthesis of your coupled product. In this instance, we've just shown a simple biaryl compound. Normally these processes are shown as a catalytic cycle. So you may have come across these before. So typically when we talk about these reactions, we start at the top here with the blue box. And this is where we sort of introduce our catalyst to the catalytic cycle. So TM could be something like palladium with ligand or nickel. So L for these slides, and further on, L usually refers to a ligand that's bound to that metal. The first step of these cycles is oxidative addition. Now I'm going to go into these steps separately later, but I just wanted to discuss these briefly in the context of the cycle. And this is where your aryl halides shown in the green box here are activated by the metal. There's another key step in this transformations is transmetylation. Again, this is something we discussed earlier in the context of organolithium and Grignard reaction formations. And in this case, you're transmethylating from your organometallic component of the reaction to form a palladium intermediate or a transition metal intermediate species. And the final step of the catalytic cycle is called reductive elimination, which is where your final product is formed and you regenerate your active transition metal catalyst. So again, I just want to go through different steps of these and just show you the important factors that help us predict reactivity and also generate reactivity in this process. So first of all, you need a catalyst of some sort. So I said before, the most commonly used catalytic system involves the use of palladium metals, and these are often in the form of palladium with some sort of combination of ligands attached to them. And so ligands have a number of roles in these processes, but one of the main roles is that it stabilizes the reactive metal species, and it also makes them soluble in organic solvents. So you can have a homogeneous catalytic system rather than a heterogeneous mixture. So some common sources of palladium catalysts are shown here. These are usually commercially available. So you might have things like palladium acetate, palladium dichloride, or palladium DBA. And you'll normally combine these with a ligand. And typically in palladium catalyzed chemistry, we use phosphine ligands. So phosphine ligands are phosphorus compounds with 3 substituents. They can be aromatic substituents, shown by these examples. They can be aliphatic substituents. They can also be combinations of different substituents, like we're shown here with these biaryl type phosphine ligands. One thing they all have in common is the phosphorus has a lone pair, and this lone pair can bind to a metal. So it can form a bond with the metal and help to dictate the reactivity and also make the metal soluble. And depending on what groups you have bound to the phosphorus, it can have a massive impact on different stages in the transition metal cycle, or the catalytic cycle, sorry. Normally though, we can just use reagents and ligand combinations that we can buy off the shelf. One common one is this, it's called palladium tetrachus, which is palladium with 4 triphenyl phosphines, and also palladium dichloride bis triphenyl phosphine. And for most purposes, these combinations work quite well. But as you go to more challenging couplings, you might need to get ligand systems that are more reactive. So for instance, in this reaction here, we have shown a palladium source, which is palladium dichloride. If we treat that with 2 equivalents of this tri-terbutyl phosphine ligand, we can in situ generate our catalytic system. Now, these alkyl groups here, the reason we might use something like this rather than the aromatic rings of triphenyl phosphine is that they are more electron donating than the aromatic rings. So they push electron density towards the phosphorus, making that phosphorus lone pair more electron rich. They also have an advantage of being sterically hindered, which can also impact parts of the catalytic cycle. So when we talk about electron-rich ligands, this aids that initial oxidative addition step, which is the start of the catalytic cycle. And I'll go into these in a little bit more detail later. And these sterically hindered ligands can help to stabilize the transmethylated complexes that you form in the transmetylation step. And also sterically hindered ligands promote reductive elimination to give you your product at the end of the catalytic cycle. So I'll just go through the oxidative addition step again. And this is, like we discussed with the formation of Grignard reagents before, in this case, it's the transition metal can add into a carbon halide bond, which we typically refer to as RX. And that's just shown in this green box here. And the typical reactivity in this case of the halides is that iodides are more reactive than bromides, which are more reactive than chlorides. So what happens in the case of, if we look at this top scheme here, if we have a palladium species that has 4 ligands, it's got 18 electrons in its octet, so it's a typically unreactive species. So what we need to happen before this to undergo any sort of reaction is it has to successively lose ligands from that complex. So that's what we've shown as first arrow here. We lose a ligand to give a 16 electron complex. We lose a second ligand to generate this reactive 14 electron complex. And then it's these palladium 0 reactive species that can then add into the carbon halogen bond to give a new 18 electron sort of stable organometallic species. And so in this case, our palladium is going from an oxidation state of 0 to an oxidation state of 2. So that's undergoing oxidation and it's adding into that alkyl halide bond. So in addition to halides, so your iodine, bromine, and chloride, we can use, or X can be what's known as a pseudo halide, and that includes things like sulfonates. So these are just sort of sulfonate esters of phenols, so they can easily be prepared from phenolic compounds, which is quite advantageous because phenolic compounds are readily available. And so a common one you'll see is this triflate shown on the left. So this is just trifluoromethane sulfonate or triflate. It's also represented with this OTF shorthand. So it behaves like a halide as it can form a leaving group, and this sulfonate stabilizes the negative charge quite well. There are other variations which are also coming out, such as nonylphthalate, which is just a longer chain version of the triflate, and things like fluorosulfonate, which is a simpler version there. So the role ligands play in the oxidative addition step, I was talking about how we can have electron-rich phosphines. Electron-rich phosphines can stabilize this 14 electron intermediate by adding electron density into the palladium metal, which means it's more reactive than towards the alkyl halide. So it's got a better share, essentially a better share of electrons to add into that bond. So the electron-rich ligands can make your palladium 0 species more reactive. And depending on some of the ligands used, they can also help stabilize that reactive intermediate, so it's formed a lot easier in solution as well. And also another benefit of having strongly electron donating ligands is that they can react with some of these more unreactive halides like a chloride. So chlorides are, again, there's a lot more available than bromides and iodides. The transmetylation step, similar to what we discussed before for the organometallic reagent preparation. Here we take an organometallic reagent like a Grignard, for instance, and it gets transmethylated with the 18 electron palladium species. And what we end up from that is a palladium intermediate that has now two of its ligands are our two different carbon groups that we want to eventually couple. And so this step is typically driven by the formation of the metal halide or metal halide salts, so represented by MX, which will go into solution. So this is not an equilibrium process. And this is often the slowest step in the catalytic cycle. Many organometallic reagents are tolerated in different processes, such as magnesium, zinc, boron, tin, and silicon. And often what you'll find is that the transition metal coupling reactions are grouped together based on the organometallic species that is used. And then they'll often be named after the person who discovered that reaction. And in some circumstances, we can consider hydrogen as the metal in that step. So as I mentioned before, reductive elimination is the final step of this pathway. This is where we actually form the carbon-carbon bond that we want. And it also regenerates our palladium zero species, which is our active catalyst, which then proceeds again through the catalytic cycle. So just shown in this blue box, we have this 18 electron palladium 2 species, which can eliminate these two carbon-carbon ligands to regenerate our 14 electron palladium zero species. So our palladium 2 is being reduced to palladium 0, and we are eliminating our product through the formation of a new carbon-carbon bond. And sterically hindered ligands, I mentioned before, can help drive this process because they can be used to push these two separate groups closer together on the metal, and they're more likely to then react in this manner. There are also other transition metal reactions called carbometallation and beta elimination, which hopefully I'll introduce later, but they're not relevant to this first section just yet. So one, as I said before, a lot of our couplings are named by the person who discovered the reaction and grouped into the organometallic, which is being used as part of the reaction. So the Stille coupling is the cross-coupling between your alkyl halide shown in green, and in this case we use organostannane organometallic reagents. So these are contain a tin to carbon bond, and they can be used to generate our coupled products. So some of the advantages to this chemistry is that organostannane reagents are quite stable. They generate products in excellent yields with a variety of substrates and functionality. And you can also form the alkyl stannanes in high yields as well. They have a major disadvantage in that the tin is actually very toxic. It stinks as well. So it's not that pleasant to work with, especially if you happen to get some on your gloves and pull your gloves out of the fume hood. You won't have many friends left in the lab if you do that. It can actually be quite difficult to remove traces of tin from your reaction product, even after multiple purifications. And for this reason, the Stille coupling is not widely used in drug discovery programs, because if you have something that's quite toxic, such as tin, even as a trace component of your active or compound you want to assess for activity, the tin can actually lead to erroneous results in your assays. It can actually interfere with your biological assays. So to form organostannane compounds, we can do this from Grignards, again, highlighting the utility of Grignard reactions. We can treat Grignards with tin tetrahalide compounds in ether to give our organostananes. And what you might notice here is that the tin usually has 4 alkyl groups here. So you're putting 4 alkyl groups onto the one tin, but actually only one of those alkyl groups will participate in the reaction. So it can actually be sort of quite wasteful in terms of your alkyl halide or Grignard component of that reaction. You can also lithiate. So here we've got an example of lithiation by deprotonation and adding a trimethyl tin chloride to form our organic tin reagent. We can also use something like this triflated enol compound and use palladium cross-coupling to generate our tin intermediate for further tin cross-couplings. So this is just the mechanistic cycle for our Stille cross-coupling. So again, we have our pre-catalyst or catalyst, which enters the catalytic cycle, undergoes our oxidative addition step with our alkyl halide or pseudo halide of choice to generate this intermediate. Next, our tin compound undergoes transmetylation. So we can see one of our R groups is now transferred to the palladium, and we generate this tin halide species. Then in this case, we've shown how our R groups on the opposite side of the palladium center. This can rearrange so that they are on the same side or cis to each other, and then this can then undergo an elimination step to give our product. There are many examples where this Stille coupling is useful. We can see here that we can have on the left our organometallic component can be an alkene, and we can use that to couple with acid chloride here to generate this enone compound. Again, this doesn't, like a Grignard, won't react further to generate tertiary alcohol. We can use alkynes as well to generate these alkyne aromatic carbon-carbon bonds. You can also use aliphatic systems here and cross-couple with another aliphatic system to generate this diene-like structure. And we can also use aromatic stananes to couple with alkene or pseudo halides to generate this sort of arene alkene type carbon-carbon bond. So it's a very useful reaction. It just has many drawbacks in terms of the toxicity of reagents. Grignards themselves can be used in cross-coupling reactions as the organometallic reagent, and this is referred to as a Kamada reaction. So again, here we have alkyl halide, which reacts with a Grignard to give our coupled product, and that usually uses palladium or nickel for this reaction. And we know that Grignards can be quite easy to prepare. There are many reagents to do that. It's quite a common process. The reactions can actually proceed at room temperature with this this procedure. So you don't have to, if you've got substrates that are particularly sensitive to temperature, you might have more chance of making your product using this method. They're more reactive than zincates, which is an Negishi reaction, which we'll cover later. But as we've shown before, Grignard reagents lack some compatibility with different functional groups. So that would be anything with a slightly acidic proton, like a phenol or even an amine. And we know that Grignards are quite reactive towards alkenes, ketones, so you wouldn't be able to do this reaction with a ketone functionality. And we also know that Grignards are quite moisture sensitive, so you have to do these reactions under rigorous anhydrous conditions. Organozincates can also be used in cross-coupling reactions, and this is known as the Negishi reaction, where our organometallic component is this zincate species. So again, advantages to this reaction is zincate reagents are typically easy to prepare, and these can usually be done by transmetylation. So from an alkyl lithium or a Grignard reagent. Reactions can also proceed at room temperature in some cases. And zincates are softer, like cuprates are softer nucleophiles, so they have greater compatibility with functional groups than your Grignard reagents, for example. So they won't typically react with ketones and that sort of thing. So it's quite a facile reaction. It works quite well. Although it does also have limitations. So secondary alkyl zincates are difficult to prepare. And the zincates can be very moisture sensitive, although there have been recent advances in this area. And zincates have a short shelf life. So you can't prepare a lot of your reagent and just keep it in the fridge or on the shelf ready to use for your next reaction. So you have to generate the zincate every time you want to do the reaction, which can be quite tedious. And zincates, again, there are many ways to form this. So we can do an oxidative addition of zinc into an organohalide bond, which is shown here using a zinc and copper alloy, but also transmetylation, which we showed before. I'll just skip through this because it's sort of the same catalytic cycle, very similar catalytic cycle that we viewed for the Stille coupling before, but just to highlight some of the reactions that we can do. Here you can see using a aldehyde, which wouldn't be compatible with the Kamada conditions because it would react with Grignard, so we can form biaryls which have aldehydes here. We can also use this to form carbon bonds to aliphatic groups using something like an allyl halide. And again, we can swap our sort of partners around. So here we've got the aryl halide, but we can generate this primary zinc, aliphatic zinc compound to generate another carbon bond between an aromatic ring and an aliphatic chain. And a similar sort of thing here, we can generate this benzyl zinc type compound to react with an aryl chloride of this pyridine derivative to give this benzylic type compound. So you can sort of start to see that there's quite a number of different applications to these chemistries, but probably one of the most popular reactions for cross-coupling that you'll come across is known as the Suzuki reaction. And in this reaction, we are using boronic acids or the esters of boronic acids as our cross-coupling partner. And so this is just a typical boronic acid ester. This is known as a pinicolato boronate ester. So the pinicol is this this aliphatic portion here. Both of those will participate in the reaction. So the advantages of the Suzuki reaction, you can use alkenes, alkyl groups, or aryl boronates as your boronate coupling partner. Boronates are typically quite stable, and there is a large number of these are commercially available, so you don't have to prepare a lot of these yourself. They're highly compatible with other functional groups, which means you can carry a lot of functionality through the reactions on your coupling partners. And it's probably the most universal and widely used palladium catalyzed coupling reaction. In addition, say in comparison to the Stille coupling, none of the byproducts or reagents are toxic, and anhydrous conditions for this reaction are not required. In fact, water is actually is required for a lot of the successful reactions. Some disadvantages is that coupling of alkyl boronates can be difficult at times. So things like a methyl boronate or a cyclopropyl work well, but other alkyl groups don't work so well. And some heteroaromatic boronates are unstable. So for instance, if you have a pyridine ring and you have your boronate in the 2 position, which is next to the nitrogen, that's actually quite an unstable compound and will decompose before any reaction takes place. So boronates, or boronic acids and boronates, can be prepared by a number of methods. I'm just showing here, we can actually take an aryl halide, such as an iodide or bromide, and react that with this pinicolato diborane compound. using palladium catalyzed conditions to actually generate our substrate for our palladium catalyzed Suzuki reaction. And also we can do this via transmetallation by generating our organometallic reagent, transmetylating that with an alkyl borate, which in the presence of mild acid can give you your boronic acid ready for use in cross-coupling reactions. The catalytic cycle is very similar to what we'd shown before, but I'll just I'll skip through to one important part of that, and that's down here in the bottom left. I mentioned before that this reaction can be done in water, and how it's actually useful to have water in this reaction, because the boronic acid itself won't undergo transmetallation with the palladium to generate your palladium intermediate with the 2 carbon groups. You actually have to use a hydroxide base or another base in water to generate hydroxide, so that hydroxide can actually add to the boron to give you your tri-substituted boronate intermediate. And then this species is now active to transmetallation. So this will now transmetallate with your palladium intermediate to give your your palladium intermediate with 2 carbon ligands, which is then ready to reductive eliminate and re-enter the catalytic system. So this also is makes this sort of chemistry a lot easier to do, because you don't have to worry about the rigorous exclusion of moisture from the system. And it's quite powerful chemistry. So just some examples here. You can use triflates for this chemistry, showing here's this indole triflate, works quite well to give this substituted indole derivative. This heterocyclic iodide can be coupled with a furan boronic acid in good yields. This boronic ester here can couple with aryl halide to give these sort of aldehyde containing compounds. So again, this is showing the versatility of this reaction, as these reactive carbonyl compounds survive the conditions. And you can also get selectivity between halides, shown in this example. So on one end of this nitrogen heterocycle, we have a chloride, the other end we've got an iodine. And in this reaction, only the iodide reacts with the phenyl boronate to give the desired product. And this sort of chemoselectivity can be exploited between iodine and bromine as well. Both are suitably reactive for this sort of chemistry, but the iodine will react first. So in this example, we have this iodobromobenzene, which reacts with our boronic acid shown in red to give this intermediate compound. And we've got exclusive reactivity between the iodide and the boronic acid, leaving this boron still available for another cross-coupling. So in this example, they just add more boronic acid into the same reaction mixture and continue to heat, and we actually get the second addition to the bromine atom. So this chemoselectivity is, in this instance, has allowed 2 reactions to happen one after the other, so it avoids steps necessary for isolation and purification of the compounds, which is advantageous. We've just got some examples here. Just the takeaway message from this is that you can use alkyl halides and boronate esters of alkenes, and the stereochemistry or the cis-trans geometry of your starting materials is maintained in the product. So if you have a trans iodide, in this case, it's maintained in this part of the molecule. And in the second coupling here, shown at the bottom, going to the bottom, we can see that our cis alkene is actually maintained when we use a cis boronic acid. So this just shows that you can maintain your alkene geometry and you don't get isomerization during the reaction, which is very, very useful, particularly in terms of natural product synthesis. So to now we've just covered some synthesis of biaryl compounds using a number of different palladium catalyzed cross-coupling reactions. But this isn't the limit to what we can do. We've also seen that we can use a number of different alkenes and alkynes in some of these reactions. But in each case of the reactions that we've covered so far, we've had to generate the organometallic coupling partner for this reaction. So this is fine. The reaction works well. It's often easy enough to do, but it's much more advantageous if we can just use the alkenes or the alkynes directly in our reaction rather than having to generate the organometallic. So in this next section, we'll sort of move away from this biaryl synthesis and look at another or two other reactions where we can generate different carbon-carbon bonds where we don't need to form our organometallic. So depending on time, we'll cover I'll go through the Heck reaction and also the Sonnegier-Scherer reaction, and time permitting, I'll just touch on some heteroatom carbon bond formation reactions. So just before I get into the Heck and Sonnegier-Scherer, I just wanted to cover two other reactions which can occur at transition metals. And these are carbometallation and beta elimination. So for carbometallation, just shown in the scheme here, this is where we can add or palladium carbon species can add across a double bond. So this happens initially from this 18 electron complex. We can lose a ligand, which leaves a space available for this alkene to then follow on what is called a pi complex. So in this case, the metal is forming bonds with the pi electrons of that alkene. And then what happens next is your carbon group will migrate. So in this case, it's migrating to the less sterically hindered end of your alkene, and the electrons from that pi bond will form a sigma bond with your palladium metal, and that's shown by this species here. So I'll just also note that this is a 16 electron complex. It's actually got a vacant spot for another ligand, which can just be taken up by another ligand to form this sort of stable intermediate. Beta elimination is essentially, you could view it as the reverse of carbometallation, but we're going to be talking about it in the context of the elimination of a beta hydride group, and this will give us a new pi bond in this reaction. So when we talk about beta hydride as the group which migrates, we refer to this as a beta hydride elimination, and this forms our new pi bond. So here we're just starting from sort of our intermediate that we showed at the end of the last slide. 18 electron complex, quite happy. It can lose a ligand. It opens up this hole on the palladium species, which then means that the hydrogen can migrate towards that position. And at the same time, the sigma bond between the palladium metal and the carbon can reform this pi bond in this pi complex. So this is again quite a happy complex, but this alkene can then dissociate and just give you your new product or your desired alkene and reform this 18 electron species with another ligand. So in these reactions, we'll often have base present, and that can eliminate, you've got now hydrogen and a halide on your palladium metal. The addition of base can actually remove that as the HX salt and regenerate this reactive species, which then re-enters your catalytic cycle. So the Heck reaction, this is actually probably one of the first sort of palladium catalyzed, transition metal, palladium catalyzed transition metal cross coupling using catalytic amounts of palladium. And in this reaction, it takes an aryl halide, which we've shown in green, and reacts with an alkene to generate these styrene type products. So the advantages of this, particularly with respect to your alkene component, you don't have to generate an organometallic reagent here. It's tolerant of a wide range of functionality, and it can also be performed in non-anhydrous conditions. Disadvantages is that you typically need an electron withdrawing group attached to your alkene here to facilitate the coupling. So in the context of the catalytic cycle, a lot of this is the same as what we've covered before, where we get the palladium 0 species that oxidatively adds to the aromatic halide bond And here is where your alkene comes in, and you get this coordination pi complex, followed by migration of your aromatic ring and rearrangement of the bonds from the pi complex to give this sigma intermediate, which, as you can sort of see from the arrows here, can now undergo this beta elimination, beta hydride elimination, to give your alkene pi complex with your newly formed carbon-carbon bond. This can then dissociate to give you a product, and base will come in and convert this palladium-2 species to a reductive elimination. So these are just some examples shown here where we can form this, take styrene and convert this to the aryl, form another aryl carbon-carbon bond. You can use aryl bromides here with acrylic acid to give this cinnamic acid compound. And again, you can also use this aldehyde conjugated with an enone for this reaction with the iodide to give this tertiary substituted alkene. And these can also be done intramolecularly to give new ring systems, as shown here for this natural product like scaffold. Similar to the Suzuki's before, these reactions can react chemoselectively, so your iodides are more reactive than the chlorides, so that will typically react first, followed by the chloride as this second reaction. Your cis-trans selectivity is maintained with your aryl halide component, and you typically get trans selectivity for your alkene component. And I just, sorry if I'm starting to race through things, I'm just trying to get through this next reaction before coming to the end. So another powerful reaction is known as the Sonic-Ashira reaction. This is the coupling of an sp2 halide or an aryl halide with an alkyne to generate a new carbon-carbon bond with between your alkyne and your arene. So again, the advantage of this procedure is to prepare, you don't have to prepare your organometallic reagent, whereas the alkyne in this instance. Again, it tolerates a wide range of functionality, but on some occasions you can actually have the alkyne reacting with another equivalent of itself to give the bis alkyne compound, which can limit the yield of some reactions. So again, the catalytic cycle is very similar to what we have seen before, where we generate our palladium-0 species, which undergoes oxidative addition with our aryl halide to give our 18 electron intermediate. The main difference for this process is how we get our alkyne into the coordinated to the palladium species before it undergoes reductive elimination. And so the key to this one is the presence of copper within this reaction. So copper is actually able to form one of these pi complexes with the alkyne. And when doing so, it makes this proton on the alkyne more acidic. So we discussed this or had alkynes before, we could show that these are weak acids could be deprotonated by carboxylic acid, by organometallic reagents with a pKa of around 25, but an organic base like a triethylamine is not sufficiently strong enough to deprotonate that. However, when the copper coordinates the alkyne, it greatly increases the acidity of that proton. It can be removed by the inorganic base to generate the salt, and then the copper migrates to the terminal position of that alkyne. So now we've generated our organometallic in situ for this reaction. And then this organometallic reagent can then undergo transmetylation, followed by rearrangement and reductive elimination to generate your disubstituted alkyne and regenerate your palladium your active palladium-0 species. So we've just got some examples here where we show we can use triflates generated from this catechol compound to generate this alkene. Also, we can show that we can react with an aryl iodide as benzofuran using this terminal alkyne. Interestingly enough, if you treat this product with base, you can actually eliminate acetone and give another terminal alkyne, which is available for cross-coupling. So it's a masked alkyne or masked acetylene. And we can also, it works well on heterocyclic systems as well. And once again, if we have an alkene coupling partner in alkene iodide, we maintain that cis-trans selectivity, so we can generate cis and trans alkenes reproducibly. So I did have a few more slides, but it's not these were sort of going beyond the carbon bond forming step. So I'll probably leave it here at this point. So we've just sort of seen how, powerful this transition metal cross coupling can be. Using palladium in particular, we've been able to show that we can use a variety of alkyl halides and a variety of organometallics to generate unsymmetrical aryl type compounds, substituted alkenes, dienes, acetylene containing arenes, and also things like this enine type compound. So you can generate quite a vast number of products depending on the judicious choice of your reagents, your coupling partners, and your catalytic system and ligands. So hopefully this has been of interest, and hopefully you've managed to take something from this. And once again, I just thank you for the opportunity to deliver this lecture. And if anyone has any questions, I'm happy to try and answer them.
Thank you, Tren, for a very comprehensive lecture, where you have given us a lecture regarding CC bond formation, covering organometal chemistry, carbonyl chemistry, and also transition metal catalyzed cross coupling. So yeah, I think now we are moving to the discussion session. We have two students that have raising their hand. Probably I will give the first opportunity to Hanifa Ayu to give a question to Dr. Tren Aston.
Okay, first of all, I'm so sorry I cannot turn on my camera right now. I have some technical difficulties, but I want to ask, I'm actually curious about the first session. We discussed about the carbonyl compound, and the reaction was occurred in a very low temperature, right? But in the second session, it was form the same bond, which is carbon-carbon bonds, but it was occurred in a very high temperature or in a room temperature, and even still use a catalyst. And my question is, what properties does the both compounds have that can make a huge difference in the reaction that reaches the temperature?
Sorry, which bit were you referring to in the first session? Generating the enolates.
Can you explain more, Hanifa? Can you explain more?
Yeah, so in the first session, the carbonyl compound reaction, there's also some reaction that form a new CC bond, new carbon-carbon bond. And in the second session, we also form a new CC bond, which is formation of the aryl compound, but it has a very different condition for the reactions. And I assume it is because the properties of both compound, but I want to get more explanation, like what the properties of the compounds that can make the reaction occurs with very different conditions.
Can you get the question? Yeah.
So hopefully I'll be able to answer the question. Yeah. So with the carbonyl chemistry, some of the reasons why we're doing it at low temperatures was to prevent the reactive intermediate you might generate from your starting material reacting with another molecule of your starting material before it has a chance to react with another substrate, if that makes sense. So that was typically with the formation of enolates, where you might use low temperature to deprotonate your alpha carbon to generate your enolate. And using low temperature makes that enolate that you form unreactive, essentially. And it only sort of becomes reactive once you add in another component of your reaction and increase the temperature. So that's what will happen with sorry.
Yeah, I think it's answer, Hanifa, yeah?
Yes, thank you so much. But can I ask one more question?
Yes, please.
Okay, so I saw the quench term in the first session, quenching with acid. And from what I know, quenching is related to fluorescence if I'm not mistaken. And is it the same terms, or if it's not, then what does it actually means for quenching with acids, quenching with electrophiles?
Yeah, okay. So when we talk about organic reactions, quenching is a term we use when we're trying to stop the reaction, I guess. So this might be typically after the reaction's complete, after you monitor the reaction and you consume all your starting materials, you might generate, in say for the instance of the Grignards, you might generate an alkoxide with a magnesium salt. So we quench, that's quite basic still. So it's actually can't be isolated by itself. So we might quench that with the addition of water or acid. And what the quenching process done is it, protonates your tertiary alkoxide in that case and gives you something that you can isolate, but it also will have the effect of decomposing any additional reagents you might have there. So if you use an excess of a Grignard reagent, you will want to quench that excess Grignard reagent because that can be reactive. It might react with something in your workup, for instance. So it's a way we say the term quench when we're referring to stopping the reaction, essentially. With fluorescence, it's a slightly different concept. So with fluorescence, obviously your compound absorbs some energy and then, your electrons go up to a highest, vibrational state in the molecule. And when that comes down, you usually get the emission of light. So when you talk about quench in terms of fluorescence, you're actually preventing that emission step. So you're giving the molecule another pathway to lose the energy and without the emission of light. So yeah, they are quite two different things. And apologies for not sort of mentioning that clearer, but you tend to just sort of normally go into some sort of typical terminology that we might use sort of day to day. So hopefully that clarifies that for you.
Okay, thank you so much for the explanation.
Yeah, thank you, Hanifa, and thank you, Trent, for the answer. So, Muhammad Fahri, do you want to ask a question directly, to Trent?
Okay, can you hear my voice?
Yes, I can.
Okay. Hi, Mr. Ashton. Thanks for the lecture. And by the way, I couldn't turn my camera on because there was a problem on it. Okay, so in organometallic reagent reaction, we know that different treatment on the reactions, for example, the setting of the temperature of the system or the solvent that we use, sometimes they give us a different product. Let's say in carbolithiation, when we set the temperature at -78 degrees Celsius, you will get the product A, and if you set the temperature at 23 degrees Celsius, you will get the product B, or maybe you can get the product A and B as a mixture if you set the temperature in different conditions, let's say. So my question is, what is the strategy to be done on choosing the treatment to the reaction as we can get the specific product and prevent from the unwanted product, especially in organometallic reagent? So yeah, thank you in advance.
Yeah, so one thing I sort of didn't mention is that organometallic reagents can also react with the solvents that they're in as well. So often we will perform those initial transmetylation reactions at the low temperature so that the organometallic reagent we use and also the organometallic reagent that we generate don't react with our solvent and lead to, reduction of reaction yield. So typically that's why you'll see the reactions performed at low temperature first. And then from there, it all sort of becomes more substrate dependent and what other portions you have in the molecule. So if you are able to maintain the temperature at the low temperature, you can affect one form of reactivity, or you might, as shown in one example, you warm it up and can generate something different. When you actually also add an organolithium to solution, you do generate a little bit of heat in the reaction mixture. So that can also impact if you don't actually have an effective cooling bath, that can impact some of the outcome as well. So the temperature initially is there to make sure that you can generate your reactive intermediate. But after that, it just depends on what you're wanting to achieve, whether you maintain that cold environment to dictate the reactivity. So did that sort of explain? Does that help?
Is it okay, Pak Hari?
Yes, yes. Thank you in advance, Mr. Ashton.
Okay. So another rising participant, Dea Paujia, you can ask directly to Dr. Ashton.
Okay, thank you. Good afternoon, Mr. Ashton. First, I want to say thank you for the lecture and the opportunity to ask. And I'm sorry if I can turn on my camera because of the bad connection that I have. My name is Dea. I want to ask you a question about the coupling reaction in the CC bond formation. I've read that the coupling reaction using phenyl halide is a stereospecific reaction. Why does that can happen? Thank you.
Yes, that is because you get, so I'm presuming when you say stereospecific, actually I probably might get you to clarify. Do you mean stereospecific at the position on the arene it occurs?
Yeah.
Or
Yes,
stereospecific?
as a stereospecific reaction that I've read that using phenyl halide it will be the stereospecific reaction, the result, the product, I mean.
Yeah, I guess so. They're stereospecific because, so depending on which component or how complex your coupling partners are, when you have reductive elimination steps or migration steps, a chiral group, so something that has your stereochemistry, will migrate from the metal to the carbon with a sort of transfer of electrons on the one face of that chiral center. So they won't come off the metal, so they can't come off and epimerize. So they maintain their chirality because the migration occurs all on the one face of that chiral center.
Yeah, Dea, does it answer your question?
Yes, it's really helped to answer my question.
Yeah.
Thank you.
Yeah, okay. Yeah, actually there are more than 40 questions in the chat box, but we have a time limitation. Probably I'm going to read one question. It's
Sure.
coming from the organometal chemistry. It's coming from Yoga, because I found that several questions are quite similar. Yeah. Yoga would like to ask what factors that can affect the stability and reactivity of organometallic compound.
It's a good one. Yeah, so I guess the difference in the electronegativity between the carbon and the metal. So if there's a greater share of electrons in that bond towards the carbon, it can make it more basic. And that becomes one of the key problems, is how basic it is and how susceptible it is to protonation and reduction of that bond. Also, a lot of the transition metal intermediates are quite prone to oxidation from things like oxygen, which might be in the reaction. So a lot of these sort of things can often be countered by having some bulky ligands around your metal to prevent sort of oxygen getting in, or ligands which are particularly good at stabilizing metals with low oxidation states. But yeah, also excuse me, we can go to softer organometallics, which become like the copper and that sort of thing, can start to become more, less basic with the change in electronegativity, but you can also have different groups on the metal which might reduce some of the electron density away from the metal as well, and also help to reduce the basicity and reactivity of the organometallic. And I think I mentioned zinc's being reasonably unstable at some point in the lecture. There's some recent work being done recently where they generate organozinc compounds with pivolate ligands, which are actually solids at room temperature and can be weighed out open to air and that sort of thing. It won't react with moisture in the air and things like that. So often just tailoring the electronics of the system, or perhaps providing steric bulk around an organometallic, will help protect it from decomposing.
Yeah, thank you, Dr. Ashton, for the answer. I think, yeah, it has answered the question. Actually, I really want to read all of the question, but since it's already 2.5 hours, and some of the student also has another lecture, and I think you have another task as well. So probably, if you don't mind, like several questions, I will select and I will send it through your email. Is that okay, Tran?
Yeah, sure, I can do that.
Yeah, okay, thank you very much. So yeah, and to all of the students, if you want also to learn again about what we have just obtained from this lecture, you can also check on YouTube, because it's already in our Department of Chemistry YouTube for a better understanding of this subject. So Dr. Tran Ashton, thank you very much for a very interesting lecture today. I believe it's really beneficial, yeah, for all of us. It has given us a better understanding, particularly for this carbon-carbon bond formation. But before we close this session, I would like to ask all of us to take a photo session. Yeah, okay, so I would suggest all of the students and also lecturers to open the camera. Just one, yeah. Yes, please, student, open the camera, because we will take some photo together with Dr. Ashton. Yeah, so I'm waiting for all of students to open the camera before we start. Yeah. So the next slide as well, yeah, we have 3 slides, 3 screens. So please, if you can just open the camera, yeah. Okay. Yeah, I think we can start with the first slide. 1, 2, 3. One, two, three. For the second slide. For the third slide, 1, 2, 3. Thank you very much. Yes, once again, Dr. Tran Ashton, thank you very